Okay. There will be another makeup lecture for your coming written test. I'll also make it available to you as soon as I can, so you can definitely plan your time to study for that. But makeup lecture, they are not really covered in the actual written test, but they will be covered in the exam. So it definitely will be your best interest to really make sure you study them in time and ask questions. Assignment number 3, I believe you'll be due next week, so you got to make sure you do it. And then assignment number 1 and 2, they are not exactly covered like a programming test, but in the written test, I might ask you maybe something for comprehension. So just make sure you go over the solution and make sure things will make sense to you. That's a little bit different way to assess your understanding. And written test will be next Thursday this time. It will be, again, Williams Small Center, the same place and the same format, the same time as well. But this time we'll be using E-class for the written test. So make sure you bring your mobile phone because you're going to do the mobile verification for E-class. And also make sure you bring your ID. And of course, got to double check your PPY login is actually okay, right? Please read the guide about the written test. And it says everything you should know. And also for the coverage. So what we talk about today will also be covered for next Thursday written test. All right, so guys, let's talk about this one here. I wonder if that might be helpful to you. I'm more than happy to give you a review session. You can ask me questions about the written test as you study in person. One possibility would be, of course, I can try to find a time, maybe outside our classes, but it's really difficult to find a time that will work for both you and also me. We can do that, but another way to do it, let me tell you what I propose. You can tell me how you feel like. It could be that next Tuesday, which will be March 17th. So we still meet in the Aqueduct East, the usual classroom, but we can make it a review session for your written test. You can just ask me any question you like. I'm going to record a session as well. You can still review the material afterwards, but no agenda. You can just ask me any question you want to ask for the written test. But instead, I will actually give you the lecture recording instead to study, but that material is not going to be covered in the actual written test. So you definitely got time to really catch up, but you got to make sure you catch up in time, all right? Lecture video instead. Are you okay with this proposal, or you rather we do the normal lecture, but I will need to find another time for review session? You guys are the ones who usually show up to the in-person class, so we can make a decision now. Any preference? Review session like in the actual class, right? And I'll give you some video to watch, okay? Are you guys okay with that? Okay, awesome, okay. That's good. Okay, it's confirmed, right? I think you guys' opinion I value the most since you come, okay? So next Tuesday, March 17th, we'll still meet in the same place, but it's going to be a review session, right? I can bring you a question, really, right? I'll see if necessary, I can even give you like a Google Doc. You can even put your question beforehand if you feel comfortable, right? We'll see how that goes. But I'll give you also the lecture recording, maybe over the weekend. You can also make sure you actually study that before Thursday's lecture, before next week's lecture, right? Anyway, I'll write it down in the E-class announcement. All right, sorted. Okay, good. Right, let's do a quick recap and then we'll continue. Okay. All right, so last time we said for this particular page about how you can initialize a generic array, so that there's a lecture video actually to show you how you can understand that workaround line. I'll leave it to you, right? It's also part of the learning outcome to really know how to implement generics in Java. And we spoke about 2 more properties about lower bound and upper bounds for external versus internal nodes. So basically, the minimum case versus the maximum case will be exactly the minimum case for number of nodes, and also maximum case for the number of nodes as well. So minimum case will be a slanted tree. Maximum case will be a full binary tree. So you can think about all the cases are kind of related to each other. So make sure when you study for your written test and exam, try to study all these properties together. They are not really isolated. They are definitely related. And then we spoke about, we spent quite a bit of time about mathematical induction. I think that's also very important. We don't emphasize on mathematical induction as much compared with 3101, the algorithm course. But I think this course is important for you to, number one, understand the basic principle about what steps are necessary for mathematical induction. Number two, this might be the only example we would do for mathematical induction. So I would say also study this example here very carefully. Maybe during the exam period, I can give you maybe another exercise to try it out about mathematical induction. I think this is really important technique for you to know how to judge about the correctness of properties for recursive structure. Okay. And then we spoke about proper binary tree, right? Just another consideration about whether or not your application will really give you a proper binary tree. You can look for the discussion for that back on Tuesday. Okay. All right, so this is something I would like to do a little bit more exercise on, and then we can move on. Okay. This is kind of the last topic for binary tree lecture, and then we can move on to a little bit more recursion, intermediate recursion. We'll talk about tree traversal. The big picture is, given a tree, which can be arbitrarily big, let's say a general tree. You simply don't know at each level how many children do we really have to visit or how many subtrees we have to visit recursively. So we want to have a systematic way to visit every node in the tree. So there are, given a general tree, you got two choices. Either you can do pre-order or you can do post-order. Pre-order means I want to visit the current node first, the parent node, and then I'll visit each of the child subtrees one by one. But for post-order traversal, I kind of reverse the order. Before I even try to visit the current node I start with, the root or the parents, I try to visit recursively every child subtree from that particular node, and then that particular node, right? You can see the order is exactly flipped for the traversal, right? So we did pre-order in detail using the family tree example and also the expression tree example. For the post-order, I think we did this one here, right? The family tree. And also for this one here, we can do it together again today, right? Just to conclude the topic. And then I want to also talk about in-order traversal. In-order traversal is another way to systematically traverse the tree. However, you want to remember this. In order for you to apply in-order traversal, the tree itself must be a binary tree. It cannot be just like a general tree. If you have more than two children for any of the nodes, then in-order traversal just is not applicable, right? So just remember, it's going to be only for binary tree for in-order traversal. Do you have any questions in general about understanding the traversal? Anything? Okay, so just do more exercise then. All right. Okay, so these are the two examples we did on Tuesday. So why don't we try post-order, right? So that's also the pre-order we did, right? And why don't we try the post-order, right? Let's do it together, okay? I'll make it a little bit zoom in, right? Hopefully it's a bit bigger for you, right? The way I would suggest, when you are not as proficient doing this, there's one way you can try, okay? So let's say I want to do the post-order traversal. Let's say starting from this particular node. Think about the minus sign there is the parents, right? And I should do the post-order traversal for this particular subtree, followed by the post-order for this particular subtree. After these two, I'm going to visit the actual parents, right? So what I will do is I'm going to say this will be the post-order for the left subtree. The post-order for the left subtree. And there will be another post-order traversal for the right subtree, followed by the parent node, which is the minus sign. All right? So that's okay? Okay? Let's try to dive a little bit deeper. Because for this one here, before you get proficient in processing like a large tree like this, you can go as deep as you like. Let's go a little bit further. Okay? Let's talk about doing the post-order for this. It's a recursive process. So for that one there, let's say I got this will be the root for that particular subtree. So that one there should really come the last, right here. And then I should really do the post-order traversal for this one here, and the post-order for this right subtree right here. So I'm gonna get another two right here. So this will be the post-order for left subtree, and also the post-order for right subtree, okay? Okay, I think somehow I spelled it wrong. LST, RST. Okay, left subtree and also right subtree. And then what would be the post order for this one here, right? That one there, let's go even deeper, right? Just for this branch, let's go as deep as we can. And then for that one there, it's going to be basically the multiply sign over here. And then the post order for this, followed by the post order for this, right? So this should be simple enough. What is the post order for this little tree here? Anybody? Children and then the parents. Okay, well, I'm talking about this little tree. What should be the post order? Anybody? Would like to give it a try? Any idea? Yes, please. Yeah, now maybe. You're exactly right. Yeah, be confident, right? That's what you need for the actual test, right? 3, 1, and then plus, right? That's exactly right. Thank you. All right. All right, so that one will be 3, 1, plus, right? And then, also we got the right-hand side, which will be 3. Okay, so what I have is this. 3, 1 plus correspond to here. The 3 here correspond to here. The multiply is right here. All right? So that's really the kind of little exercise you want to really do in isolation and convince yourself. You need to internalize the process. All right, for the rest, we can do a little bit quicker. What would be the in post-order traversal for this? Anybody would like to give it a try? This one here, a little bit larger. Go ahead, please.
9, 5 minus 2 plus.
Yeah, I agree. So basically, this one here will be 9, 5 minus, and then 2, and then plus. Exactly right. So 9, 5, 9, 2, and plus. And then you can see after this and this, which correspond to left subtree, right subtree, we follow by the divide. All right. All right, finally, this one. I'll just give you the answer. Okay. That one there will be 3, 7, 4 minus, multiply, and then 6, and then plus, right? So think about this part over here is right here, followed by 6, which is here, and then plus, right, and etc. Right, try to do that exercise maybe as many times as you like, or you can even try to change the structure of the tree. If you're not exactly sure what the final outcome should be, there are 2 ways you can do it. Number one, you can try to encode the Java implementation for pre-order, post-order, and see what output you got, and check against it. Or just come to my office hour and ask me. Yeah?
So when we're doing the traversal, do we always go to the left child first?
Okay, okay. Do we also always go to the left child first? I want to be more accurate here, okay? From left to right, that's for sure. But since we talk about general tree, let's say if you got 5 children, in that case, you got to go to first, second, third, fourth, and fifth, always from left to right, right? Because if you look back here, we say for loop, for children, right? The children here may just be an array or simply linked list. So we'll go from left to right. All right, finally, we got in order traversal, right? So this time here, we're going to do left child, parents, and right child. Guarantee it's going to be only 2 children because in order traversal is only applicable for binary tree, okay? All right, for this one here, I'll give you the answer, but I'll just go a little bit deeper, okay, slightly. So we're going to do left subtree over here. That one there, I'll first put it. 3 plus 1, multiply 3, divide, and then 9 minus 5 plus 2. Okay, I'll try to show you some correspondence. Think about this part here is the 3 plus 1. 3 is over here. In the middle, we got the parents. All right, and then we got divide right here. And then right subtree will be 9 minus 5, 9 minus 5. The parents will be plus, and then right subtree, just 2. All right, good. All right, and then finally we got this minus over here in the middle, and then I can do the right subtree right here. Okay, that one there will be 3 multiply 7 minus 4 plus 6, but you can double check. I would say if I simply give you some example tree and do the pre-order, in order, or post-order traversal, it should be some question you should be able to answer rather quickly. Okay. All right, that's about tree traversal. Any questions? All good? All right, good. All right, and then you will just see one more set of example about pre-order, post-order, and also post-order, pre-order, in order, and post-order. Okay, so for example, you got some paper that you may have to write. Then you just got the table of contents over here. You can do either pre-order, post-order, and etc. Okay, I'll let you look at that example as well. Only pre and post-order, because apparently this is not binary tree. It's a general tree. You got more than 2 children at some level, so you cannot use in order. But for this one here, you just got, for example, another expression, right, that can show you the in order traversal. Okay, and that's it about binary tree and general tree. Guys, any questions, please, before we move on? All right, so now we are good for binary tree and general tree, and we are moving a little bit deeper and deeper into the tree. But before we get to binary search tree, which we will cover after your written test, okay, the Tuesday when we resume the lecture after your written test, we're going to talk about binary search tree. But for now, I want to talk about another lecture here. We kind of went over recursion part 1 in the beginning of the semester. I would like to talk about part 2, right? There will be some intermediate recursive structure or algorithm that you have to know as well at this level, right? We're going to talk about 3 things, okay? We're going to learn about intermediate recursive algorithm. You know, I say that they're not really advanced. They are not difficult, right? Conceptually, I'm going to help you to build an intuition, and also they also give you all the Java code to implement them already. So you're just going to play with them to see if you can make any variants from them. All right, well, first of all, we're going to talk about binary search today, okay, for sure. Binary search, you may have heard about it before, but we're going to see how we can do binary search on some linear collection, let's say an array. Okay, we're going to see how we can do that. We're going to talk about intuitive idea. We're going to talk about runtime, time complexity, and also Java implementation and trace it, right? We're going to talk about all the aspects for binary search. And we'll talk a little bit about something called merge sort. So I kind of listed about all the sorting algorithm you're supposed to know after you before you graduate from this course, right? So merge sort is another one. We talk about selection sort, insertion sort already. So merge sort and quick sort is what we're going to cover in this recursion part 2 lecture. One more, which is called heap sort. That's something we'll get to once we talk about binary search tree, heap, etc. Right? That's around towards the end. So these are the 5 sorting algorithms you'll learn from this course. These are the standard ones CS or software engineering graduate should know. Okay, we'll get there. And quick sort as well. I think most likely quick sort will cover that in the lecture video I'm going to give to you, right, on Tuesday, since we're going to turn that into review session. Okay. All right, binary search. Okay. Why don't we go directly to, you can definitely look at the slides. Okay, you'll be from slide number 3, right? This is just about the sorting problem, right? So we'll talk about non-descending order, right? That's something we spoke about earlier, but we can go directly to what the problem is. One thing to really note, without binary search, right? Let's say you just given an array, you want to search for an element, it's going to be linear time because simply don't know where the element is. Could be all the way to the end. So you're going to take about n iterations to get to the end of the array. That one's simple. But now for binary search, we have to make some assumption, an important assumption about the input. If we can make that assumption there, we will be able to substantially improve the running time. I can tell you even now from linear to log n. Okay, it's a big improvement, but we'll see how exactly we can do it. Okay, you'll see about the description about base case, recursive case is a recursive algorithm, but I'll walk you through in a moment. I just want to show you the structure for the slides. And then you will see the Java implementation here. I'll also walk you through about every line and see how we can figure out the time complexity based on the Java implementation. Okay, it's going to be it's going to require a little bit of different mindset when you actually want to work out the running time for recursive algorithm because there's no loop right here. Right, we're going to talk about it today as well. And then and then that'll be the math detail, right? So for binary search, it's going to be from slide number 3 to number 6, right? That's something we're going to walk you through. the first part for today. And then we'll see how much time we get left. We'll talk about merge sort. Okay, okay, let's get to the intuition. Okay, right here. Let's say we are given an array right here. So we got 0 index all the way to a dot length minus 1. We go from smallest index to the largest index. Okay, and there's a very important precondition, meaning that if this condition is not satisfied by the input array, you cannot even do binary search. You will just get the wrong result, very likely. Okay, the array we are given should be sorted in non-descending order. If you recall, we actually talked about the 4 different combinations, right, for the sorting order. That's something you want to review as well, for your written test and exam. Okay, for non-descending, that means we can stay the same or we can just go ascending, right? So, very quick reminder. When we talk about non-descending order, it can be stay flat, or you can go ascending, or you can stay flat, and it might go ascending again, right? So that's kind of the pattern we assume, right? How does binary search really work, right? Okay. The idea really comes from how you actually look up a word in a dictionary. Have you guys ever used something like this? Dictionary? You have, right? Maybe in the high school, in my days, they also got like a dictionary contest just to see how fast you can actually look for some words in the dictionary. Let's say I want to look for some word. I'll just randomly, maybe I'll go in the middle. Let's say here I see the letter M, but maybe the word I'm looking for, let's say Oxford. O will actually come after M. So now I should really go to the right side. So that means it's guaranteed. This is N. I don't really need to go to the left side because it's got to be less than M. So if I want to go for O, I should really go to the right side. Effectively, I already truncate all the search space on the left-hand side by half. Right? I keep going until I can hit the search. All right? So let's now make it a little bit more abstract over here. That's really the key idea for binary search. Let's look at this array. Okay? Let's now introduce some terminology, and we'll turn that into code. First of all, we got 0 here, and we got a last index over here. We say that the entire array is called an initial search space. This one here. So we go from 0 all the way to a dot length minus 1. This is our initial search space. And you can think about it simply just n, right? Depending on how large the array is, okay, or how many pages the dictionary is. Okay? And then we're going to go right to the middle. Okay? It's like we flip the page right to the middle of the dictionary. Okay? How do we calculate where the middle is? Well, simple calculation. You just go for the average between 0 and a dot length minus 1. Right? You just a dot length minus 1, and then minus 0, and then divided by 2. You find exactly the middle ground. Okay? So we say that this particular value over here is the middle value. This will be the middle value. Let's say we are calling search on, we're searching for some particular value, let's say K. So binary search. Let's say we're implementing some method. We simply say search for K. What we do is we try to compare K against the middle value. If K and the middle value exactly match, we have found it. Awesome. Return right away to say true, we have found it. Let's say if K is somehow not exactly found it. In that way, we have to decide, given that the array is sorted, we know that here, all the values over here, guaranteed to be less than or equal to the middle value right here. Agree? Because it's sorted. And also, all the values over here on the right-hand side guarantee to be larger than or equal to. larger than or equal to the middle value, right? So this will be the middle value that we're talking about. Given that the middle value is not really matching k, now we want to know whether k is less than or larger than. If k that we are looking for is strictly larger than the middle value, now where should we go? Do we need to even go here? We don't need to, because given that k is strictly larger than the middle value, in that way, given that all the values to the left of the middle value is less than or equal to, guarantee k cannot be here. So we can truncate this search space. So we can go directly to the right half. If the element does exist, it can only be in the right half. So we go there. It's a very important logic about binary search. You want to make sure every time if you decide to go to either left half or right half, you're not really omitting the possible places where the element can exist. Right? That's a very important insight. Please make sure you make note of that and make sure you're convinced. All right, let's now write it down, some idea. So here we are saying that if k larger than v, that means if k exists, it must be to the right of the middle value. So that means we can focus on just this half. But there's another possibility. Let's say here, if k is actually less than v, if k exists, does exist, it must be to the left of the middle value. All right, so we either go to the left or go to the right. So once we trace the code for one example, you will also see exactly how it works. Okay. So let me also write down the steps that you're going to need, and then give some idea about the running time. Okay. So number one, you have to access the middle of the search space. For example, right here, if the initial search space is the entire array, we go just for the middle value. Okay? If we do decide to go to the right-hand side of the array, so this will be the new search space. In that case, we calculate where the middle is and compare that against k. If k happen to be smaller than this middle value, then we search for this left. Otherwise, we search for this right, and so on. We keep going until we found it. Or maybe the search space is simply empty. In that case, we can conclude that the element simply does not exist. Okay. So step number two, we're going to compare the k that we're looking for against the middle value. And there are three possibilities. If k exactly equal to the middle value, that means it has been found. You might just return true. If k is strictly less than the middle value, in that way, we have to go to the left-hand side. Okay, go to the left half. Recur on the left. Excuse me. So here I'm being a little bit vague about what do you mean exactly recur on the left. For example, let's say I'm here. Currently, this is my new search space. I calculate where the middle is. And k is strictly less than this middle value. That means I should really recur on the left. But how do I specify the range of this left search space for me to recur on? So that's something that requires some precision. But we'll see that when we get to the Java code. It's not that difficult, but you have to keep in mind specifying the range about the left and right area for us to recur on is also very important for binary search. Third possibility, if k is strictly larger than the middle value, then we recur on the right. So we got possibility number 1. And then we got possibility number 2. And we got possibility number 3. Okay, these are the 3. So another thing I want to just mention very quickly, but you will see that also once we start tracing the code. When we try to work out the time complexity for binary search, you have to worry about how large is the search space. So we start with n elements over here. Once we compare against the middle value, we can decide. Let's say we go to the right. So this will be the new search space, which will be n divided by 2, exactly half. And once we calculate the new middle value, we decide to go to here. This will be the new search space. How large is that? Definitely smaller than n divided by 2, but how large exactly? If we go to another half. N over 4? Yeah, exactly. So we keep going. So the search space will be smaller and smaller until it reaches maybe 1 or 0. Okay? So what we do is, let's now put the size of the search space. Okay? In the worst case, because sometimes you might just be able to find the element and return already. But let's say in the worst case, you may have to keep recurring until you reach the base case, like a 1 or 0 for the search space. Okay, the size for the search space, you start with n, and then you go to n over 2, and you go to n over 4, all the way to possibly just 1 or 0. That'll be the base case. So when we actually work out the time complexity for this binary search algorithm, that's something you will see as well. That's a mathematical pattern we have to see. We'll see that today for sure. Okay. Yeah, for this one here, you may not be able to see just yet, but we're going to trace the code. Okay. Any questions so far? Binary search? Good. All right, let's now talk about Java. Okay. I'll also make the code available to you. I think I'll do that right after the class. Okay. So for binary search, it's a recursive method. So there's a public one and also a recursive one, right? Pretty much like how we did for assignment number 1. Okay. So let me show to you. Just to start with, we have binary search, which takes an array. And this array is assumed to be sorted, right? Again, it's a very important assumption. It is sorted in non-descending order. And then we're looking to search for the key k, right? So here, this is the k that we actually mentioned in the previous page, okay? And we are saying that initially we're going to pass call by value, the array reference, and 0 to the smallest index and largest index. So that will specify exactly this entire search space initially, right? So this part here, you can think about from 0 to here. This will be the initial search space of size n, given that the size of the array is n, right, initially, okay, from smallest index to the largest index. And this is the actual recursive algorithm. Binary search helper and binary search helper. First of all, let's convince ourselves, why is this method recursive? Because it calls itself at some point. So here, it calls itself right here. And here, it also calls itself, right? So these are the two places. Pretty much like if I got the middle value not exactly matching the k, I need to either recursively search on the left or I recursively search on the right. These are the exactly two places I might have to call recursion. Okay, you can see the correspondence. Right? All right, let's now take a look at the base cases. So you will see that these two are the base cases. So from larger than 2, right? That's something we studied earlier about recursion part 1. So that's why I assume you already know, right? When from is larger than 2. That means we got empty range. It's as if the search space is empty. So there's no way your key is in the empty search space. So that's why we just return false. When from exactly equal to 2, so we got a range of just one element, in which case it might be the hit, or it may not be. In that case, just return whether or not array at that index is exactly equal to the key. This one here can be true or could be false. Right? So you can think about these two base cases are really the 1 or 0 size for the search space I spoke about earlier. Right? Those are the base cases. What about recursive case? Okay, let's now also visualize that at the same time. Okay? So what we have is we got middle. You can think about this like a middle index. Okay? So we got the middle here, which will be the from and to, and I calculate what where the middle is. So that should be from plus 2 divided by 2, right? That's just the middle index. Straightforward. And then I want to retrieve the middle value accordingly. So think about this is my middle value right here, the actual elements there. Okay. And then I got two possible cases. Either I can go this way, or I can go this way. Okay? There are two cases. Since it's like an if-else-if structure, I cannot go to both ways at the same time, right? I cannot. Either go to the left or go to the right. Let's look at that. If key is strictly less than the middle value, right? So that means the key may be here. May be here if the key is strictly less than the middle value. Okay? In that case, what do? We want to make sure we recur on exactly this range over here. And how do we specify the range? Should be from to, what's this index? Middle minus 1, right? That's what you will see. So you see from and middle minus 1. This is the new search space of size n divided by 2. Because the entire search space may be n, in that case we could go to half, which would be n divided by 2. Right? On the left. On the other hand, you can see that here we are trying to do if key is strictly larger than the middle value. So that means we might go here. So here, key may be here if the k is strictly larger than the middle value. Okay? In that case, we're going to recur on this range over here. In that case, what should be the from value? Middle plus 1. All the way to the 2. So from here to here. So middle plus 1 to 2. So this will be the new search space in the other scenario. Space of size n divided by 2 on the right. Okay, so let's now make it a little bit more colorful. Think about this will be one scenario. This will be another scenario. You go for this scenario if the middle value, okay, let me say it again. You go to this left side here if the k is strictly less than the middle. In that case, you go from to middle minus 1. In the case where the k is strictly larger than the middle, in that way, you go to the right-hand side. That will be middle value plus 1 to 2. Right? So you go either way and do the recursive call. Of course, there's also the else part. If it's not less than, it's not greater than, then it must be equal to. In that case, we don't have to do any recursion. Okay? So this part here about the else. This one here is we have found it. K is exactly equal to the middle value. That means we have found it. No recursion needed. Okay. Any questions? I'll give you a little bit look ahead. Okay. This is all good. This idea is very important. You are able to go to one side without worrying about the other side. Later on, once we resume after your written test, we're going to talk about something called binary search tree. So tree is not a linear data structure. However, if we try to set up the tree, binary tree, in a way that's going to satisfy so-called search property, we will be able to do something like this, but with some additional constraint. That's something you will also have to study, maybe for the exam, right? But I want to give you a little bit look ahead. This is not going to be studied in isolation, but we're going to compare doing binary search on an array that's sorted versus doing binary search on a binary search tree later. So these are the two things you want to connect them, properly. Okay, we'll get there a little bit later. Okay. Why don't we take a short break, exactly halfway, and then after the break, we can trace the code together about binary search, and then we can move on to merge sort. Right, two more things I want to talk about for binary search to make sure it's complete for the discussion. Number one, let's now try to trace the Java code on some input array, and I'll give you some exercise to try it out. Hopefully that'll make things just very concrete for you. And then we're going to move on to talk about how you can derive the asymptotic upper bound for recursive method like a binary search. Binary search is kind of a simple case, but it still can be a little bit tricky when you're seeing it, seeing that. So I'll go very thorough, very slow. But once we get to merge sort and quick sort, those will be more complicated for the derivation, but that's something hopefully will be much gentler for you to do. Right? Anyway, one thing at a time. Let's now try to do a tracing. Okay? This I got two examples over here. This part here, right? Exercise for you. Right? We're going to do this part together. Okay? But similar. I just want you to try more. So for the right-hand side, exercise for you. Okay? But we're going to do left-hand side thoroughly with you. All right? The left-hand side. Let's say we're given this array. Question could be, is this array suitable for binary search? You're going to check, is this in the non-descending order? It is. 3 less than or equal to 6, 6 less than or equal to 9, etc. Right? That's why you can check first of all. Okay? So this is a sorted array. And then we want to call the search method, right? Remember before the break, we talked about search and also search helper. Or you can call it binary search, doesn't matter, right? Search is really this public method here. And the search helper, binary search helper, is this private research helper method that we're talking about, okay? We start with this, and then we say that call by value, we pass the A. So A is what we are looking for. It's more like the entire thing we want to search within. And we got 18 over here. So think about 18 is the key that we're looking for. As you can see, 18 exists in the array already. So eventually, we should really expect to see true. Imagine that if we don't have binary search, if you only got linear search using a loop, the running time will be big O of n. Right? So let's do binary search. And then we're going to call, if you remember, it's going to be initially the search space will be from the smallest index to the largest index. So it's going to be from 0 to 8. So I'm going to do annotation on both sides. Initially, the search space is going to be the entire array. Okay? Think about it's going to be just n. So we got from 0 to 8. Okay? So this will be the search space. Okay? Right here. And another thing just to note right away, so that you can see the A here is called by value. So A here, A here, A here, all refer to the same array. We never create any new array. And also the key that we're looking for is always 18. 18 here, 18 here, and also 18 here. So when you try to trace the binary search, it's only the range of indices that's going to change, right? One insight to notice right away. So we got 0 and 8. From 0 to 8. What should we do first? Where is the middle? So we're going to do the following. The middle index, the middle, I would say n, will be 0 plus 8 divided by 2. which is 4. That means we have 4 right here. That's a middle index. The middle value, accordingly, will be 8 at index 4, which is 15. And we ought to decide, should we recur on the left or should we recur on the right, right? We compare to see if 18 is strictly smaller or strictly larger than 15. Obviously, strictly larger, so we should recur on the right, okay? I write it down. So 18, which is the key, strictly larger than the middle value 15. So that means we should really go to the right. Okay? Now, if we want to go to the right, we want to make a recursive call on the helper method. Now, what should be the range of indices? Since we want to go to the right, you should not include 4 anymore. It should be middle index plus 1. Should be 5 all the way to 8. So that's exactly what you saw earlier about middle plus 1 and then 2. Right? That's something you can check later yourself. Okay? So that means we're going to go for the index 4 plus 1. And then all the way to 8. Okay? 4 plus 1 and also 8. So this is why you will see 5 and 8 in the next. Effectively, we are narrowing down our search space from 5 to 8 right here. All right? Hopefully, still making sense. Now, for this m divided by 2, roughly, the size will be n divided by 2. And let's now talk about how we execute this recursive call. That one there, again, we got to calculate what's the middle index for here. When the number of elements are actually even numbers, so you cannot find exactly the middle, but that's okay. In practice, as long as you're either one to the left or to the right of the actual middle, you're fine. Okay? So let's just do the same calculation. So we're going to figure out right here, the middle index will be 5 plus 8, and then divided by 2. And since we're doing Java, it's like an integer arithmetic, so you don't really calculate like a precision. So 5 plus 8 would be 13, divided by 2 would be 6, right? If you do a double, you'll be 6.5, but you don't need that, okay? All right, once we get 6, so the middle value, so 6 is right here. The middle value will be A at index 6. A at index 6, which will be 21. So now in this case, we got to compare 21 against the 18 that we're looking for. So now this time, should we go to the left or right? Left. Because 18 is strictly smaller than the middle value. So if it exists, it must be on the left. In this case, we just hit it. All right? So here, we're going to write it down. So 18, the key, is strictly less than the middle value, 21. So that means we go to the left. Okay? If you go to the left, it's basically going to be the from value over here, 5, and also the middle index, which is 6 minus 1. So that'll be from 5 to 5, exactly just the space for one element. So you can check later. So that'll be from and the middle minus 1. Okay? So we're going to go for this new range. 5 over here, and then 6 minus 1. So that's a final range you will have, 5 and 5. So that will correspond to just this part over here. All right, so go to the left. So now this is a base case because we only got one element in that particular range. So what should we do? What we do is you can see that that one corresponds to when the from is equal to 2, base case. We check to see whether that element there is equal to the key. In this case, 18 is indeed equal to the 18 we're looking for. So we found it, return true. If this one here, for example, is 17, we return false. All right? All right, so over there, we're going to have A at 5 equals 18, right? So that means return true. Okay, that's what we have. Okay, that's a binary search. So the most important thing for you to really see as we do the tracing, we start with this range over here. And then we shrink it down to half. And then we shrink it down to another half. Right? Keep going until you reach search space either 0 or 1. And the search space over here is roughly about n divided by 4, roughly. So just keep shrinking down the search space size. Questions? Clear? All right, you got to do an exercise of the other one to make sure. Okay. Okay, once this is done, let's now talk about time complexity. Right? This might be new to most of you, but we're going to do it. It's a simple math exercise, actually. Okay. Whenever you're given some recursive algorithm, let's say binary search, and also later on merge sort and quick sort, the way you kind of figure out the running time is a little bit different. Okay. This is the standard. We are basically defining some running time function, and then we're trying to solve it. That's something we're going to do. And the T here, capital T, simply stands for running time, just capital T. And then we're going to see the input size n over here could be 0, can be 1 for the base cases. But what if we get to the recursive case? If the input size is simply n, how can we write down the corresponding time equation accordingly? That's something we'll see. Okay? So running time function. Okay? But let's see exactly how this can be worked out. The way to work it out, we got to go back to our code for Java. Okay? Let's see 3 different cases. We have our base case number 1. This is our base case number 1. And this is our base case number 2. And over here, this is our recursive case. Right? 3 cases. So that's why you will see the running time, which is t. We're going to try to see, depending on the input size, we're going to give different answer. Okay? Let's start from here. The initial search space right here, from 0 all the way to the maximum index, this will be simply just n, right? And then we want to see, depending on what the value of from and to is, we can decide either the search space is 0, 1, or something larger. Okay. So given this, we want to know what is the running time. Okay, in general, that's something we are trying to solve. Okay. Let's look at each one of them. The first one, when from is larger than 2, this means the search space is simply empty. In that case, we just return false. And we know that return is simply a primitive operation, so which will be constant. So we can simply say the running time for when the search space is 0 size, the corresponding running time would just be 1, because returning something. So I can simply put 1 over here. Are we okay with the first case? Right? We're just saying that for binary search, the running time will be capital T. And the argument inside the T, which can be 0, can be 1, can be something larger, which we say n. In the case of 0, we just return false, just 1. Okay? The second base case, we say that we're going to return, again, this particular computation. It's like an array indexing relational operation and also return, like a 3 primitive operation, which is still a constant. And we can also say the running time in the case where we got only 1 element, because from is equal to 2. It's a range of 1 elements. That would be, you can say 3 here, but you don't really need to. As long as it's a constant, you can just say 1. Because eventually, the multiplicative constant can be dropped. You just only keep the highest term. Okay? That's also 1. All right, so these are the 2 base cases. They'll be also very similar when you talk about merge sort and quick sort. Very similar for base cases. It's really a recursive case that's tricky. Okay, let's look at a recursive case. This part here about calculating the index and also the middle value, right? Just computation, right? Basic arithmetic calculation. Big O of 1, right? That one you agree. And then let's look at them, the other 2 cases individually. Either we get to this branch or we get to this branch. Either way, right? Either we try to make a recursive call on the left half, or we try to make a recursive call on the left half. Okay? This will be recur on the left half. And this will be recur on the right half. And as we said earlier, the search space will be shrunk down by half. Each one of them will be n divided by 2, right? The corresponding running time will just be t, but now it will just be n divided by 2. And here as well, n divided by 2. Given that the search space is cut down by 1/2, right? Think about this part here is about perform binary search on half. Also this one here, perform also the binary search on the other half. Okay. So now what should we put over here? I'll give you 2 choices. Choice number 1, we might say, since we got either half or half, right? It should be the first half plus the right half for the complexity. It should be the left half plus the right half. And plus whatever we did for calculating the middle value, right? Middle value and middle index. And then plus 1. That's option 1. Option 2, I argue that you only go to the left or you go to the right. You don't necessarily have to go for both every time. That way, I would just say t n divided by 2, and then plus the basic work. So I got option 1 and option 2. So these 2 will give you very different results for the time complexity. But now the question is, which one is the correct one to adopt? I'll pause and I'll let you think. The question is, should we go for option 1 or option 2 for the t of n case? Go ahead. Option 2? How come?
Just because we would ignore the right side.
How are we guaranteed you're going to ignore the other side?
Because the number is strictly larger or less.
I agree with you, but how about the code itself? How can we be guaranteed is the case?
The I plus 1.
I plus 1? Uh-huh.
Or middle plus 1.
Mm-hmm.
Or middle.
I definitely agree with you. Okay, so you basically say you can be middle minus 1 and middle plus 1, right? Okay, what I'm really looking for is something like this. If you think about if and else if, in any programming language, if else if tells you that if I already go for this branch, guaranteed this branch will be ignored. If I somehow didn't go for this branch and this branch is satisfied, and then I guarantee just go for only one of the 2 branches. My point is, hypothetically, if I somehow say if and if about these 2, in that way you may have to argue a little bit more deeply about why I cannot really go to 2 branches at the same time. That's something you just want to have some extra argument. Okay? Anyway, but you're quite right. We should really go for option 2. So first of all, option 1 is not right. Wrong. Because the if, else if guarantees only one branch will be executed, right? So we're going to put here will be either left or right on half of the space, and then plus 1. Again, the plus 1 here, the 1 here, really correspond to the constant amount of work we have to do to really prepare to find out where the actual middle value is, and also any auxiliary like comparison you have to do, right? Just constant, right? So what we got is a list of equations like this. That's the first step. I would say typically, to really go from Java code into mathematical function like this might be the more difficult part, because somehow you have to see exactly how the equation should be laid out, right? This will be part 1. Part 2, given this mathematical equality here, we have to solve it. Because we don't really see what the running time is. Eventually, we should get to log n, but we don't see any log n in this equation here. Okay? So what we should do, the next step is based on these 3 equalities, we have to solve it. We have to solve it to obtain a so-called closed form. I'll explain that. You will see that. Closed form formula. Okay? And we're going to see that. A closed form formula. Okay? Okay, let's do it together, right? Okay, so we got these 3 exactly here. And then we're going to solve it, right? Okay. Let's do a warm-up exercise here. You got t of 0, you got t of 1. You know, if you can get down to 0 or 1 size of the search space, you just got 1. That's something we would like to boil down into, okay? But we should really start from this. This will be the more general case, okay? So let's do a warm-up exercise over here. Based on the definitions over here, what would be t of n divided by 2? What would that be? It's more like a mathematical substitution, really, right? You're given 3 equations, and now I'm asking you, I want to know what's really t of n divided by 2. So what you want to think about is n divided by 2, what kind of substitution can I make? N divided by 2 doesn't really match 0 here. Also, doesn't quite match 1 here. But you can think about n divided by 2 as a whole can be the n itself. After substitution, we can get something according to this definition. But what would that be? Yeah, go ahead.
T of n over 4
Plus 1? Okay. You're getting there, but not exactly. We want to be very precise. Okay, let's see. Yeah, let's give it a try. Okay. So here, so that means n divided by 2, I'm going to replace it over here by n divided by 2. Okay? Actually, you're right. I beg your pardon. I'm thinking ahead about something else. Okay? So here, that means the n here would be substituted by n divided by 2 over here. So that means it will be t of n divided by 2 and divided by 2. Divided by 4. And then plus 1. Okay? So you're right. Okay. Guys, are we okay with this? Make sure you're okay with the warm-up. Because if that one you don't really get, you'll just get lost when I start doing the real thing. Okay? I'm saying that given these definitions, 1, 2, and 3, now for this particular size of the input, which is n divided by 2, I'm basically substituting the n here by n divided by 2, which will be n divided by 2 and then divided by 2, which will be n divided by 4, and then plus 1 here. All right, just make sure you're okay with that. Later on, when we try to solve the recurrence relation for merge sort and quick sort, we do something similar. The only difference is the actual pattern might be more difficult to really identify for merge sort and quick sort. Okay, let's do this one here, just for today. Okay, let's not do the real thing. Okay, be careful. We start with T of n in general. That's the actual recurrence relation running time we want to solve. By definition, T of n divided by 2 plus 1. The process we're going to go for will be something called unfolding the recurrence relation. Okay? Unfolding. Now, I'm basically asking, for this part over here, what would that be? Exactly what you just suggested, right? That part there would be equal to T of n divided by 4 plus 1. And then don't forget the plus 1. I'll pause. Make sure everybody's following this first derivation. Okay with this? Okay? One more. Okay? We cannot see the pattern just yet. One more. And of course I make some typo here. Okay? That should be exactly here. Okay? I do apologize, right? It does make a huge difference, right? Let me say it again. You can see the T of n divided by 2 is exactly here. So I put it here. Right? The plus 1 is not part of the size of the T, which I made a mistake. Right? Just be careful. All right, let's try to unfold one more time. Let's say it will be equal to, and for this part here, let's say T of n divided by 4. What would that be? Anybody would like to suggest? What would that be? Yeah, go ahead. Yeah, sure. Absolutely. That one will be T of n divided by 8, and then plus 1, just for this one alone. And don't forget about this plus 1 here. And also don't forget about this plus 1 here. All right? If you kind of follow, that's really good, but I can tell you based on your fellow students' experience last year, you really want to do it from scratch on your own. I'm pretty sure you make some mistake, even from step number 1. Okay? You really got to practice. Okay? That would be my advice. But let's continue. All right, so usually when you're trying to unfold the recurrence relation, after 1 or 2 unfolding should be enough. Now, we should really pause and think about, if keep doing this, what do we really want to achieve? Right? What we're having here is the input size over here is n divided by 2. We make it half into n divided by 4. Make it half into n divided by 8. We're hoping that eventually, if we can get to T of 1, in that case, we don't need to do any more unfolding because T of 1 will just be 1. That's what we're hoping, eventually. All right? So let's now, with that understanding, eventually I want to get to T of 1. From n divided by 2, n divided by 4, n divided by 8, I want to get to T of 1. And then I know that it's going to be a bunch of plus 1s. But I don't know how many just yet. For that one, we need to see the pattern. Okay? It's going to be plus 1, plus 1, plus 1. But now the question is, how many? How many? All right. This will be the most important step to really see, because eventually we want to get to t of 1. And then after t of 1, we know that we got a bunch of plus 1. Okay, let me just say that this one here, t of 1, we know that it is just 1. But what about this part over here? We're going to see exactly how many 1s we should get. And at this point here, since I kind of told you binary search, the running time should be log n. You cannot just conclude, oh, we got log n once. It is true, but how do you see that? We want to see some convincing argument. In this case, you want to go back to the actual value for the input size. It's going to be a similar strategy for merge sort and quick sort. N divided by 2, n divided by 4, n divided by 8. If I look at 2, 4, and 8, there is some pattern over here, because every time it's going to be double about the value for the denominator, right? So let's go back here and try something here. So think about the 2 here is 2 to the power of 1. The 4 here, 2 to the power of 2. 8 here, 2 to the power of 3. And then I can see the pattern here, because when I have exponent 1, I have a single plus 1. When the exponent is 2, I have 2 plus 1s. When the exponent is 3, I got 3 plus 1s. All right, so that's good. And now I'm basically asking, when 1 here is the case, how many plus 1 should I get? I basically just have to rewrite the 1 here in this kind of format, so I will be able to figure out. But let me go from there, all right? So let's now get to the 1 here. I'll put a star, okay? This is the part we want to figure out, okay? 1 here, we know that it should be exactly n divided by n, because we want to get to the format where the numerator is simply n. But the denominator, we want to get to 2 to the power of something. That exponent should tell me how many 1s I get. All right? And I'm going to rewrite it one more time. N divided by, okay, 2 to the power of something. Once I figure out that question mark, I would know how many 1s I get. What should that be? So we are basically asking n here and 2 to the power something. So we're really asking n equals 2 to the power of something. What is that? Well, this part here will need you to recall what you learned back in your calculus class about log. Very simple rule, all right? Again, I'm going to write it down, and you got to make sure you learn about this, well, maybe revisit this formula. You might need it again for merge sort and quick sort. Okay, I'll write it down here. So when you get 2 to the power of log n, it will simply just be n, okay? This is the rule. And why don't we try to use some example to show it, okay? Let's say, for example, let's say n is equal to 8, right? So now 2 to the power of log 8 would be, right? What is log 8? You can calculate, it's 3, because 2 to the 3 is 8. And then 2 to the power of 3 here, go back to 8, which is the exponent itself. Right? It's a little example to show. Right? It's a property you learned earlier in the math course. You're going to review that. Okay? All right, so this question mark here we know is going to be just log n. Okay? So now for this part here, we know that it's going to be t of n divided by 2 to the log n. So given that we got log n as the exponent, so we know that we should get log n plus 1s. Okay, so how many? It should be log n. All right, so let's now 1 itself plus log n multiplied by 1. It will be log n. So it will be 1 plus, we got log n plus 1. Right? So it will be just log n, big O of log n. So this is the final answer. And also the derivation is actually much more important than the conclusion we'll get, because everybody kind of knows that binary search running time will be log n. But for you guys, I do expect you to know how to derive. Right? You got time, right? It's not going to be covered. The derivation itself, I can tell you, is not going to be covered in the written test, right? You don't need to panic too much, but for the final exam, you might get something like this. So you definitely want to get familiar and proficient in solving equations like that. We'll do 2 or 3 more examples later about merge sort and quick sort. So if you can master those, you should be okay for questions like this on the exam. But you just got to practice, right? Okay, let me just say one more thing, and then we are good. We're good. So on Tuesday next week, I'm going to post the lecture material beforehand. You can definitely take a look, and also the makeup lecture for the actual written test. But for Tuesday, we're still going to meet in Aquadet East, the usual classroom. We'll do a review session for your written test. You can ask me any question you like. It can be about the slides, iPad notes, or even the assignment solution you can ask. All right? Okay, I'll see you next week.